Section 5. How do glaciers affect sea level? Digging deeper. How glaciers affect global sea level. The ultimate source of the ice in glaciers is the ocean. Worldwide, there is more evaporation than precipitation over the oceans. There is more precipitation than evaporation over the continents. The snow that feeds the world's glaciers forms from water vapor. This water vapor was put into the atmosphere far away by evaporation of ocean water. As the water vapor is changed into glacial ice on land, sea level around the world is lowered. As the glacial ice melts, the water flows in streams and rivers back to the oceans. This extraction of water from the oceans to form glaciers on land and the return of water to the oceans is one of the important loops in the Earth's water cycle. As such, glaciers and sea level are a closely coupled system. This means that they are strongly connected, and changes to one part of the system have an immediate effect on the other. Scientists have been monitoring Earth's glaciers and sea level rise from space for a quarter of a century. Since the Topex, Poseidon, and Jason satellite missions began in 1992, researchers have observed a total global sea level rise of 7 centimeters. That's an average rate of 3 millimeters a year. In 2016, Jason 3 was launched. From an 1,336 kilometer high orbit, Jason 3 measures the height of 95% of the world's ice-free ocean every 10 days. Because it is a measure of both ocean warming and loss of land ice, sea level rise is an important indicator of human-caused climate change. Glaciologists have a good idea of the total volume of ice in the world's glaciers. Almost all of that ice is in the Antarctic and Greenland ice sheets. To calculate the volume of ice in an ice sheet, both the area and the thickness must be known. You did this in the Investigate. The area of the ice sheets is easy to measure, but the thickness is more difficult. The thickness of ice sheets is measured by echo sounding. A pulse of sound is sent down through the glacier, and the echo from the bedrock at the base of the glacier returns to the surface. The thickness can be calculated from the measured two-way travel time of the sound pulse known as speed of sound in glacial ice. Of course, for a good estimate of thickness, a very large number of soundings must be made. The ice sheets are thousands of meters thick, so the volume of ice is enormous. If all of the Antarctic ice sheet were to melt, sea level around the world would rise by about 60 meters. And if all of the Greenland ice sheet were to melt, sea level would rise by about 5 meters. As recently as 20,000 years ago, in terms of geologic history, an instant, ice sheets covered vast amounts of land. They covered Greenland, Antarctica, much of eastern and central Canada, the northern part of the United States, and large areas in Scandinavia and Russia. At its maximum, the Laurentide ice sheet in Canada and the United States extended as far south as Missouri. Sea level around the world was much lower than now. Marine geologists can recognize the remnants of old shoreline features. These remnants are now underwater far out to sea. They were formed during sea level low stand, when the sea level is at its lowest. At that time, ice sheets were at their maximum. These shorelines are more than 100 meters below present sea level. From 18,000 years ago to 6,000 years ago, sea level rose nearly its present position. This took place in the short span of only about 12,000 years. During the long sea level stand, the shoreline was far out near the edge of the continental shelf. This is 160 kilometers or 100 miles from the present shoreline. Rivers cut valleys across the shelf on their way to the ocean. Since the rise in sea level, these valleys have been flooded and partially filled with new sediment. An example on the east coast of the United States is the Submarine Valley. It extends over 160 kilometers from the present mouth of the Hudson River in New York City all the way to the shelf edge. On the west coast, the Golden Gate Strait links San Francisco Bay to the Pacific Ocean. It is a flooded river valley. During the last glaciation, the Sacramento River flowed to the sea through the present Golden Gate. San Francisco Bay was dry lowland between two mountain ranges. Post-glacial rebound. The lithosphere is Earth's outermost layer. It is about 100 kilometers thick. It consists of rock that is cool enough to behave like an elastic solid. Like a piece of rubber or hacksaw blade, the lithosphere can be bent and stretched. However, it returns to its original shape when the deforming force is removed. Below the lithosphere is the asthenosphere. It behaves like a plastic solid. When the asthenosphere is acted upon by a deforming force, it changes its shape by permanently flowing, very much the way glacial ice flows. When an ice sheet forms, its weight bows down the lithosphere. This takes place both directly beneath the ice sheet and also for some distance next to the ice sheet. Asthenosphere material flows sideways to make room for the down-bowed lithosphere. Then, when the ice sheet melts, almost instantly in terms of geologic time, the lithosphere rises up buoyantly to its original position. In Part D of the Investigate, you simulated subsidence, lowering, and rebound of the lithosphere. You did this by placing a block of wood to represent a glacier on the slab of dough and then rapidly removing the load. This phenomenon is called post-glacial rebound. However, because the lithosphere is strong and the asthenosphere is very stiff, post-glacial rebound is slow. Large areas in eastern Canada and northern New England are still rebounding after melting of the Laurentide ice sheet. This is taking place at speeds of almost a meter per century. If the ice sheet was near the coastline, post-glacial rebound causes the sea to retreat from the land in areas near the former position of the ice sheet. This process tends to offset the rise in sea level caused by the addition of water to the oceans as ice sheet melts.